I'm happy to participate in this symposium, and I would like to continue the topic of scoring function and in docking, used in docking as an energy. And I'm going to share the results of our ongoing research, which became surprising for us, and what insights it spurred, and how we could put some, we think, global questions about it. So our motivation was to generally improve scoring. For that reason, we started from reason that in physics, electrostatic interactions are no doubt important one, and from the practical point of view, almost every tools used in drug discovery, computational drug discovery, uses electrostatic interactions, especially this concerns to force fields and much of the scoring functions. So that seems to confirm that electrostatic interactions are important. So we reason that the accurate electrostatic description is crucial for scoring function. On the other hand, we have developed for a long time our charge calculation scheme, which is based on empirical scheme based on incomplete electronegativity relaxation, and we specifically train our parameters to reproduce quantum chemical electrostatic potential map, so that the resultant charges could be used either in force fields like amber, which are physics-based, of course, and or in other applications which require charges. Among the benefits of our scheme is its simplicity, and it's fast to calculate, and the simplicity means that the scheme is robust to overfitting. And it's crucial not to overfit the parameter. So, okay, our initial plan was to just apply our scheme to calculate atomic charges to a physics-based scoring function and see how it performs. So, we choose Autodoc as a classical scoring function. It is perhaps one of the most widely used within the academician, at least within the academician research and even in industry. It is based on force fields. It already uses Gasteiger partial charges to describe electrostatics, and also there are two papers which specifically try to vary partial charges within the context of Autodoc. The first paper shows that using RESP and AM1 BCC charges, which are also trained to the same quantum chemical map reproduction, gives some improvement. And the other paper, which concerns which deals with variation of different charge, and or both papers results in that shows that the improvement is possible. So we decided that as long as we target the same level of quantum chemical map with our charges, but as the best performers such as RESP and AM1 BCC, but we achieve this with higher throughput and lower complexity. So and finally, our design to test our hypothesis, we choose the golden standard CASF 2016 update data set, core set, which contains the most strictly defined geometries, and as well as the most reliably measured experiment activities. So this is the most accurate data set of ligand receptor complexes, small molecule. The design was the main idea was to use the after-dog scoring function, which is presented in the center, and for each combination of atomic charge used in our research to obtain new values of free parameters in linear model that best fit the overall score with the experimentally known energy. That's in that way each charge scheme is weighed in the fair conditions, because the after-dog parameters were fitted to Geiger charges, not to another. So this is a graphical representation of the same thing, and here for receptors we use default Geiger charges as reference, other combinations, and here you see that Geiger and the other charges as well as other charges are used to train new models and estimate final statistics. So in short, we want to see how the replacement of Geiger charges in after-dog, which are default, by our Denner charges, which are fit to reproduce quantum chemistry map, will bring benefits which we expect to obtain according to the papers we read. And all is done in fair conditions. So what are the results? The results are rather surprising for us. First of all, when we go from Geiger, that's the designation is ligand and receptor. So both on ligand and receptor, Geiger charges are used. And when we go from Geiger to Denner charges, we actually don't see any significant improvement. There are negligible improvement, but not much. This is the scatter plot of the fitted value and reference value. This is residual errors, which are quite similar, but it is interesting to note that if we estimate the contributions from the equation of after-dog in energy terms, by multiplying the contribution we fit with the force field calculated terms, we obtained those contributions which how they sum in the equation. And we surprisingly see that the purely electrostatic contribution after the fit in each case is very small. This is the green histogram. I hope you see it at all. So with the dominating contribution coming from what is here designed denoted as van der Waals, but we understand this is the hydrophobic and shape complementarity interactions. So we were surprised, and we tried to use different charges to test is there any difference at all. But it appeared that actually we couldn't find any difference, even though we tried widely different charge schemes, starting from MMFF charges for both ligand and receptor to RESP golden standard in map quality, quantum chemistry map reproduction, and Coleman charges on receptor, as well as for AM1 BCC. And even we tried to use formal charges on both receptor and ligand, so that only the atoms with formally charged groups had non-zero charge, but all the other atoms have zero charge. But that results in almost the same statistics, in some sense even negligibly better. It was completely surprising for us. We start to think, and there are two kind of questions uh, were arising. So the first two are more the technical ones, and we observed that in after-dark scoring function, which is believed to be purely physics-based or force field-based, there is a empirical term corresponding to hydrogen bonding, which we believe duplicate the electrostatics interactions. So this is the ongoing research, and we study how we can replace it. And I won't talk now about it because we are doing it. But the second technical issue is the deceleration, which is, we believe, is rather crude in current after-dark implementation. And the phenomenon of deceleration is very important and very complex. And we think that with the contemporary computational resources, there is room for improvement in after-dark. So, and finally, the most interesting for us is the conceptual question. Is electrostatic important at all to describe those ligand-receptor interaction in solution? But I would stress it in even more. On one hand, we have physics opinion that electrostatic interactions are dominating and very long range. They are omnipresent in almost every tool. But on the other hand, we obtain that electrostatic contribution in the force field scoring function is not necessary, and wide variation of charges doesn't affect this estimation much. So some reasoning about the results. Of course, the practice says that the main driving force for small molecule ligand receptor interaction is hydrophobic interaction and shape complementarity, with some decoration of hydrogen bonding. But hydrogen bonding is hardly responsible for affinity gain, because when you consider a ligand and the receptor as in separate form, they can form much greater number of hydrogen bonds with water than we combine together. So it's not the affinity gain which make hydrogen bonds present in drugs and drug-like molecules. So it's all this is puzzling, and we try to return to the main question: what we actually seek for. Do they need a tool which perfectly predicts only affinity of ligand receptor interactions, or we more need a versatile tool which is not as accurate, but it predicts how these ligands could be proceed to drug. And we state our hypothesis is that the current scoring functions inevitably measure both these contributions, and they should be separated. I try to explain it in more detail. First, the data sets used to either just obtain parameters for scoring function, or to test their performance, obtain successful examples of ligands which became drugs, or which made it to final stages of trials. clinical trials, and inevitably such ligands are optimized as drugs, so they optimize not only for affinity but for other properties, and indirectly the scoring function which are trained on this data capture these peculiarities of ligands, so that this is reflected in the results. Another reasoning line is that some presence of hydrogen bonds donors and acceptors in ligands is beneficial due to the directed interaction that hydrogen bonding can afford, and this minimizes risk of off-target selectivity. And also, in a more specific way, to obtain the beneficial admit properties, as well as improve synthesability of the ligands. So in terms of the probability, if they think that our final goal is to make a new drug and to ensure it enters the market, so we not only need to obtain the best affinity, but also provide some drug likeness properties. And we think that current scoring function try to combine these two approach, but in some implicit way. So so we think that it is possible to think about it and split these two contribution and work with each contribution separately, and understand it. So this is the corollary, and in our case we think that electrostatic interactions and hydrogen bonds are actually maybe not as relevant to affinity gain, but are relevant to best to optimize ADMET properties in our data set, which is the best data set available for researchers now. But this is the main results, and thank you.